So with regards to the content for chapter 6, first we will look into the introduction and going into the topic of performance parameters of jet engine. Okay, so and then it will be followed by turbojet as well as turbofan. In terms of the flow of the presentation, bear in mind that we are given 3 weeks to cover the chapter 6. So we are going to go into lecture 9. We will look into introduction and performance parameters for jet engine. This is going to be covered today. And we will cover the subtopic of turbojet starting in lecture 10, and lecture 11 we will look into turbofan and summary. All right, that's the plan. Okay, in terms of the introduction for this particular topic, we can say that the designer of an aircraft engine must recognize the differing requirements for takeoff, climb, cruise, and maneuvering. All right, so normally in an aircraft design, the structure people, the mission control people, the propulsion or engine design people has to communicate to each other in order for them to decide what are the best components, especially for the aircraft engine, what are the best selection of engine types, engine requirements based on the mission profile for the intended aircraft. That is including the requirements of takeoff, climb, cruise, as well as the maneuvering. So the relative importance of this being different for both civil and military applications, as well as for long and short haul aircraft, depending on the mission, the flight envelopes, the mission for the aircraft engine designer will decide what is the best configuration for the engine. So in all type of aircraft, the engines are requested to provide efficiently the thrust force necessary for the propelling during different flight phases. Okay, like what we have just announced just now, to have a takeoff condition, what is the climb condition, the cruise condition, and having maneuvering, okay, at different operating conditions, right? Because we have to ensure the aircraft can fly in the hottest or the coldest ambient temperature, whether it is a rainy or windy or snowing weather. All right, so because aircraft cannot just be designed to fly in good weather only, right? There's no such thing as that. Right. For today, we are going to look at this aspect of performance parameters of jet engine. We will look into the thrust force. We will also touch on factors affecting thrust as well as the engine performance before we go into the aspect of turbojet and turbofan in more detail. So the performance of jet engines is evaluated through the efficiencies. We will look into propulsive efficiency, thermal efficiency, as well as the overall efficiency. I believe we have already come across this particular word, the efficiency for propulsive, the zeta P, efficiency for the thermal, zeta TH, and efficiency of the overall, zeta O. The propeller efficiency of turboprop engines is also going to be evaluated, right? Like what we have already experienced when we go through the topic of propeller, which is last 2 weeks. And fuel consumption is properly evaluated through a parameter identified as the thrust specific fuel consumption, TSFC, which is the ratio of the fuel flow rate, m dot f, into the engine to the generated thrust. So thus different jet engines may be compared, and the range of aircraft is a combined engine or aircraft parameter where the fuel consumption through the engine is coupled to the aircraft lift as well as the drag force. Okay. Let us look into the first one, 6.2.1. What is actually the thrust force that we are talking about? Thrust force is the force responsible for propelling the aircraft in its different flight regimes. Okay, so this is the most important part of having a propulsive system, whether it is a propeller type, whether it is a turbojet, whether it is a turbofan or turboprop. Thrust is the ultimate aim, meaning that we want to produce thrust so that it can push the aircraft or the vehicle forward or having a different direction. So it is an addition to the lift, to the drag, as well as the weight, represent the four forces that govern the aircraft motion. Okay, during the cruise phase of flight, where the aircraft is flying steadily at a constant speed and altitude, so each parallel pair of the four forces we already mentioned just now, lift, drag, weight, as well as the thrust, okay, are in equivalent. Lift and weight as well as the thrust and the drag. So what happened during landing? Thrust force is either fully or partially used in braking of the aircraft. So thrust is, apart from getting the aircraft moving forward, it can also be used to provide the opposite mechanism. It is a thrust reversing mechanism to slow down the movement of the aircraft to stop. Okay, the basic conservation laws of mass and momentum are used in their integral forms to derive an expression of the thrust force. The thrust generated by the turbojet can be given in this relation. So you will be seeing this equation 3.1. Okay, thrust symbol T equal to the mass flow rate of the incoming air or the speed of the aircraft, m dot a, times 1 plus f times ue, exit velocity, okay, minus u is the velocity of the aircraft, plus the pressure difference between the exit pressure coming from the nozzle, okay, to the ambient pressure times the area of the exit nozzle. Okay, so the other type of thrust can be computed, such as the gross thrust. Okay, so this is the gross thrust, what you are seeing here, m dot a times 1 plus f times ue, plus the difference between PE minus PA times the AE, exit area, momentum thrust, pressure thrust, and the momentum drag. Okay, basically all of these components are included inside equation 3.1. This is general relationship for a thrust force by a turbojet. We know that the net thrust of a system equal to the gross thrust minus the momentum drag, or in other words, the net thrust equal to the momentum thrust plus the pressure thrust minus the momentum drag. So if you refer back to the previous definition just now, okay, so you can just write what is the net thrust, what is gross thrust, momentum drag, and you will see that it is actually equal to the net thrust. The left hand side here is net thrust, the right hand side here is the other components, and it is equal to the left hand side over there. Right. In the condition of the nozzle is unchoked. What do we mean by unchoked condition? Is that the pressure doesn't have any, it can just flow through the nozzle. If it is a choke condition, the air or the velocity inside the nozzle cannot be further accelerated, and that is a choke condition. But in this particular situation for equation 3.1, it is the unchoked condition, where ideally the exit pressure will be equal to the ambient pressure, right? That's why the pressure will thus cancel. So equation 3.1 will no longer having the component of the pressure difference, right? So that is for the choke condition. When that happens, the exit pressure will be equal to the ambient pressure. That's why we could not see the component of the pressure times the area over here. That's where the thrust for the unchoked condition is expressed as equation 3.2. So in many cases, the fuel to air ratio is negligible. Okay, so some of the problems in a propulsion subject, they will highlight, okay, assume fuel to air ratio negligible. So you can just remove the component of the F there. F is the fuel to air ratio element, right? So sometimes it is negligible, so you can ignore that. And equation 3.2 can be simplified to equation 3.3. Just leaving the thrust equal to the mass flow rate times the velocity difference, right? Only that. So the thrust force in turbojet engine can attain high values as the exhaust speed is high, right? If you have UE is greater, far greater than the U, right? Or in other words, UE over U is more than 1, okay, you will have a maximum thrust force, right? In a similar way, the thrust force for two-stream engine like turbofan and also prop fan can be derived. So this is just a example of a two-spool turbofan engine. We will look into a more detailed explanation when we come across turbofan engine later on. So you have the incoming air. This is just bear in mind, this is just a half of the engine, right? Top we just, because it is similar on if we just cut it into half, so we consider only half part of the engine, right? So this is incoming air U. So only 20% of air will go into the core of the engine, where you have the fan blade, and then we have the compressor blade, compressor section, the combustion chamber, the CC, turbine, right? Low pressure, high pressure turbine, low pressure turbine, and then the nozzle. So over here you have the component of the mass flow rate exit. H means hot, okay. UEH is the velocity of the exit in hot condition, pressure at the exit in hot condition. At the same time, the 80% of air will be bypassed. This is a turbofan, okay. So you have the component of the cold element, mass flow rate cold, exit velocity at cold condition, or the bypass, the pressure exit at the cold condition, okay. So it can be expressed based on the figure 1 just now. The thrust component, thrust force can be expressed as follows. You have the hot air exhaust component and the cold air exhaust component, the area for the hot region, and the area together with the pressure for the cold region. All right. So these are the definitions and the glossary for all the parameters that being highlighted in equation 3.4. The other aspect of thrust, normally they use the specific thrust. And what is specific thrust? It is defined as the thrust per unit air mass flow rate. Okay, specific thrust equal to the thrust component divided by the mass flow rate of incoming air, okay, which can be obtained from equation 3.4, and it has a dimension of a velocity, similar to velocity meter per second. Specific thrust unit is meter per second. Right. Let us go into a typical turboprop engine. Just now is turbofan, figure 3.1. We are going to look into another figure 3.2. The high value of thrust is achieved by the very large quantity of the airflow rate through the exhaust, and flight speeds are very close. So this is a typical schematic for turboprop engine. So you have a free stream flow of air coming into the propeller section, like a disc over there. Okay, so this is m dot naught, u naught, going into the section of the propeller. You will the air will then further accelerate. It has a velocity of u1, and then this is the m dot c going into the core of the turboprop engine. Okay, so basically inside here is just like a normal turbojet. This is a just connected to a big propeller fan. Okay, and then you have the mass flow at the exit and the velocity at the exit. So that, bear in mind, the velocity is experiencing from u0 to u1 to ue. Okay, an analogous formula to equation 3.4 for the case of turbofan may be employed for turboprop engine. Okay, so in this case, we have equation 3.5. You have the thrust equal to the m dot c times 1 plus f, the air fuel ratio, times the ue minus u1. u1 is the velocity after the propeller. Okay, u0 is before the propeller. ue is the exit velocity. Okay, the m dot naught, mass flow sucked by the propeller. M dot c is part of the air flow cross the propeller and then entering the engine through its intake. Okay, so u0, u1, and e, actually, this is not u0, this is ue, are the air speed upstream, downstream, and gas speed engine exhaust. Okay, put a note there. This is ue. The exhaust nozzle is normally unchoked. Okay. Right. Let us move into factors affecting thrust. Okay, what are the factors affecting thrust apart from just now we look at the mass flow, we look at the fuel ratio, we have the velocity component, we also have the pressure and the area of the nozzle. So what are other factors can affect thrust? As seen from equation 3.1, the generic turbojet engine equation for thrust for a single stream aero engine such as ramjet or turbojet engine, the thrust force depends on the inlet and outlet air mass flow rate, m dot in, m dot out, or the exit, fuel to air ratio, f, flight speed, u, exhaust speed, ue, and exhaust as well as the ambient pressure, PE and PA. Though it looked like a simple task to identify the factors listed above, each of them is dependent on several parameters. There are other parameters that need to be considered. For example, the inlet air mass flow rate influencing both the momentum thrust and momentum drag is dependent on several variables, including the flight speed, temperatures, pressures, humidity, altitude, as well as the rotational speed of the compressor and revolution per minute, RPM, of the compressor. So the outlet gas mass flow rate is dependent on the fuel added. Okay, how much fuel being added to the combustion chamber, air bleed, as well as water injection in the system. The pressure thrust term depends on the turbine inlet temperature, okay, the flight altitude, how high the aircraft flying or how low the aircraft is flying, also going to govern the thrust, as well as the pressure, and the nozzle outlet area and pressure. And the momentum thrust is also dependent on the jet nozzle velocity. So we will look into this one by one. These parameters can be further explained as follow. Okay, we have the jet nozzle, okay, the air speed, the mass air flow, altitude, and the ram effect. The first one, jet nozzle. Pressure thrust has finite values only for choke nozzle. For unchoked nozzle, pressure doesn't provide any thrust force, where the exit pressure is greater than the ambient pressure. So this is condition for choke nozzle. Nozzles are either on the convergent or convergent divergent type. So you can just have a convergent type of nozzle or convergent divergent type of nozzle. Right? We have seen this in our earlier chapters. Only convergent nozzle may be choked. Convergent divergent nozzle does not having a choke condition. For a choke convergent nozzle where air cannot be further accelerated in the nozzle, it provides a pressure thrust, okay, which depends on both the area of the exhaust nozzle and also the difference between the exit and ambient pressure. So ideally, aircraft engine designer, especially at the nozzle part, they want to design a condition whereby the pressure of the exit nozzle is equal to the pressure of ambient. And that's ideal, but that's not always like that. Moreover, the exhaust speed itself, exhaust speed is UE, is equal to the sonic speed, which is mainly influenced by the exhaust gas temperature. So if a convergent nozzle is unchoked, then the jet velocity will attain subsonic values. For a condition of convergent divergent nozzle, CD nozzle, the jet speed may maintain at supersonic values. Right? CD nozzle are normally seen in supersonic aircraft. So we move into the next one, 6.2.2.2, the airspeed. The airspeed sometimes denoted as the approach speed or the aircraft speed. Okay, it is equal to the flight speed of the aircraft in the thrust force equation, equation 3.1. Okay, such a parameter has a direct effect on the net thrust. If the exhaust velocity UE is constant, then the air velocity is increased. Right? From this expression, then the difference between the both velocity is decreased, leading to the decrease in the net thrust. Okay. Exhaust velocity constant, air velocity decrease, you will get a decrease in the net thrust. If the air mass flow and the fuel to air ratio are assumed constant, then a linear decrease in the net thrust is enhanced. So you can see here a plot between the thrust, net thrust against the airspeed VA, right? So it is gradually, it is a linear relationship, linear decrease between as the airspeed drops. When the airspeed increase, VA, the thrust of the aircraft also it is decreased. When the airspeed decreases, the thrust is actually at the maximum. All right. The next one, the third aspect that affected the thrust factors affecting thrust is the mass airflow. The mass air flow m dot A is the most significant parameter in the thrust equation, equation 3.1 earlier. It depends on the air temperature as well as the pressure, as both together determine the density of the air entering the engine. Right? So you imagine you are traveling at a high altitude where density is less, that resulted to the less air molecules going into the engine compared to at the sea level. The density are higher, more air molecule can go into the engine. So it is just a simple uh, um, analogy to the condition for the mass flow. The more air going into the engine, the higher the thrust will be. In free air, a rise in temperature will decrease the set density. Higher temperature, less density. Thus, air density and mass flow rate is inversely proportional with the air temperature. On the contrary, an increase in the pressure of free air increases its density and consequently thrust increases. Right? Higher pressure will also increase in the thrust. The effect of both air temperature and pressure is illustrated in the next figure, figure 3.9. In brief, the density affects the inlet air mass flow and it directly affects the thrust. So you can see here there are two plots over here. One is variation of thrust against ambient pressure and variation of thrust against ambient temperature. So for pressure, the higher the pressure, the higher the thrust. But for temperature, the higher the temperature, the lesser the thrust will be. Okay, because the density is also lesser for higher temperature and the thrust will become lower because the mass flow rate will be lower. All right. Let us move into the fourth factors here, the altitude. Okay, as outlined earlier, the air temperature and pressure have significant effect on the thrust. In the International Standard Atmosphere ISA, temperature decreases by about 3.2 Kelvin per 500 meter of altitude. So this drop or decreases in temperature against altitudes is about 3.2 Kelvin consistently until it reaches 11,000 meter. Right? It is consistent decrease up till 11,000 meter. Beyond 11,000 meter, it is more than 3.2 Kelvin. It is more rapidly drop. So these relations are repeated here, but the altitude expressed is given in meter. So this is just expression for the temperature. This is also expression for the pressure. After 11,000 meter, the temperature stops falling, but the pressure continues to drop steadily with increasing altitude. Consequently, above 11,000 meter, the thrust will drop off more rapidly. It is shown in the next figure, figure 310. And this makes 11,000 meter as the optimum altitude for long range cruising at a nominal speed just prior to the rapidly increased effect of altitude on thrust. It may be concluded that the effect of altitude and thrust is really a function of the density. That's why when you are flying, for example, like 777, 777 or A380, A350, it will not go beyond 11,000 meter, not going beyond 36,000 feet. So it just cruising at 30,000 to 35,000 feet to get the optimum long range aircraft. If you go beyond that, you will suffer in terms of the fuel consumption, the operating condition for the for the engine. So this is the picture, and this is the figure 310 showing the variation of the thrust force with altitude, right? So this is at 11,000 meter. Okay, thrust is dropped when you go higher. Okay, but at 11,000 meter, it will decreases more rapidly, right? The next one is ram effect. The movement of aircraft relative to the outside air causes air to be rammed. Ram means that it is hitting the air molecule, hitting the engine inlet duct. Okay, imagine you have the whether you have a propeller fan, you have a fan blade or a propeller blade. So or a turbojet, you have the compressor blade. So air will be hitting the inlet duct, and so that will affect the thrust. And ram effect increases the airflow to the engine, which in turn increases the gross thrust. You can refer back to the relationship between net thrust, gross thrust, momentum thrust, and so on. However, it is not as easy. Okay, ram effect combine two factors, namely the airspeed increase and in the same time pressure increases of the air and the airflow into the engine. Right, as described earlier, the increase of air reduced thrust, which is denoted by curve A in figure 311. The increase of airflow will increase the thrust, mass flow, mass airflow, m dot, which is sketched by curve B, and curve C resulting the combination of curve A and B. Let us look into what are the curves all about. This is the plot between the thrust and the speed of air. Okay, VA, effect of ram pressure on thrust. You have the, this is A, okay. The higher the airspeed, the decrease in the thrust itself. For B, okay, the higher the airspeed, the higher the thrust will be. Resultant of A and B is actually this plot, plot number C. So this is A, B, and this is the C, okay, resulting effect of the mass flow. The increase of thrust due to ram become significant as the airspeed increases, which will compensate for the loss in thrust due to the reduced pressure at high altitude. Ram effect is thus important in higher speed fighter aircraft. Also, modern subsonic jet power aircraft fly at high supersonic speed and high altitudes to make use of the ram effect. Finally, okay, it is best to classify the factors we have looked just now affecting thrust into two groups. One is factors that related to the engine itself, okay, the physical engine components, okay, how the engine components or factors related to the engine influencing the thrust itself. The second group of classification is the surrounding medium, okay, the environment, the pressure, the temperature, humidity, density, and so on. So let us look into the first group. We have four factors. The first one is rotational speed, RPM, including the compressor as well as the turbine, which influence the compressor pressure ratio and the turbine work that is related to the rotational speed itself, and then the exhaust nozzle size, A, which influences the jet velocity, right? A will influence UE, and then the fuel flow rate. Okay, so we have the air to fuel ratio, F, the turbine inlet temperature, okay, TIT, turbine inlet temperature, the high temperature coming from the combustion chamber going into the turbine section will produces a higher thrust, which affect the combustor heat generation, right? And then the final one is the compressor bleed flow. Compressor bleed flow, water injection, and components performance, which also leads to increase of the specific work. So these are compressor bleed means that there are from the compressor section, the not all air that being compressed will be supplied to the combustion chamber. Some of it will be bypassed out. So compressor bleed also provide effect into the thrust. Water injection in the combustion chamber, okay, also provide just to reduce the temperature inside the combustion chamber, can also affect the thrust. Other components performance, the turbine, the compressor performance can, as well as the combustion chamber performance can also affect the thrust. So the first group does contribute to both the air mass flow rate, m dot, as well as the jet velocity. The other group, okay, which include the forward speed, the aircraft speed, which leads to thrust decrease and more fuel consumption, as well as the air density, which is influenced by the flight altitude, the humidity, hot or cold day, which influences the airflow, leading to a thrust increase if the airflow is increased, and vice versa. So that's why you can see in certain airports, so the certain hours having so many aircraft flying, very busy in the airport, and there's so other situation that there's a very rare or very few aircraft flying. So this is also resulted from the consideration of having air density. Hot air, you have less density, air density. Cold air, you have cold day, you have higher density. Okay, so it will affect the thrust. It can also affect the fuel consumption. That is what we are need to really determine what is the best situation for the aircraft engine to operate. All right, I think that's best for us to have a short break for 10 minutes before we continue on the remaining engine performance subtopic.